My name is Athanasios Papaoikonomou. I'm an ML engineer at Elastic, and today's talk will be about reranking depth in modern search pipelines. This is the agenda for today's talk. So we'll start with the overview and the experimental setup. Then we'll talk a little bit about the patterns that we have identified. Some discussion around interpretability based on the distribution of scores. The trade-off between efficiency and effectiveness, and if time permits, we'll also we'll discuss some related work. Let's start with the overview. So here we're dealing with a retrieve and rerank pipeline. So we have a corpus of size n, where n can be millions of documents. And at test time, we have a query coming from a user. We have a retrieval system like BM25, where we draw k documents out of this n, where k is usually much smaller compared to n. And we pass those documents into a semantic reranker, and our goal is to optimize their ordering. So more relevant documents should be pushed to the top. Just a note, what we denote as k here is also known as the reranking depth, and this is the term that we are going to use from now on. And the main assumption for this retrieve and rerank pipeline, so in order for this to work, we're making the assumption that the retriever captures enough relevant documents in the list that it returns. And then we trust the reranker that it will do a good job optimizing this ordering. So, as I said, more relevant documents should be pushed to the top. Here is the experimental setup. We have the retriever, which is BM25, and
Shouldn't there be a line between query and reranker also? Isn't the query an input to the reranker?
Yeah, but I'll get to that later. I mean, I have a slide for that, yeah. Here's the experimental setup. We have a retriever, which is BM25, and we use an Elasticsearch index for this. For the evaluation, we're using the BEER benchmark, and the metric is NDCG at 10. And we have a list of reranking models. There's a variety of sizes and effectiveness, some open ones, some commercial ones. We also have the Oracle reranking, which is the last one, which is just the ideal reranker, which we assume it has access to the relevance judgment for a particular dataset. So provided with a list of documents, it will do the best reordering it can be done. And we'll see in the next slides why this can be useful. Now we start with the pattern analysis. So before I talk about this Pareto pattern, I will explain the plot a little bit. So we have this two-dimensional plot. On the x-axis, we have the reranking depth, which we said it's the number k, the number of documents that we retrieve and rerank. And on the y-axis, we have NDCG at 10, which is the metric, the value of interest, the metric of interest. The black dashed line is the BM25 baseline, which is the NDCG score of the retriever, in this case BM25. And we have the curve, which shows the evolution of the metric, NDCG at 10, as we increase the reranking depth. So we go back to the pattern, this Pareto pattern. We'll explain in the next slide where we call it like this. It's the most frequent pattern. It accounts for 72.6% of the cases. And we can identify three phases. The first one is a rapid increase. As you see here, usually it ends at smaller depths, around, let's say, 100. Then it's followed by another phase where we have still increase, but at a smaller rate. And then we have a third phase, which is the saturation phase. So we might have some further increase, but at a much smaller rate. And usually it's the metric, the value is quite stable at this point. So some observations. First of all, this Pareto pattern aligns well with our prior assumption, what we said earlier, that we expect the retriever to have a high recall and have a return list of relevant documents in the list that gives back. So as we increase the pool of documents, as we increase the reranking depth, it becomes more likely to have more relevant documents in that list. And then we trust the reranker that it will do a good job reordering them, which explains the improved performance. See? So this Pareto pattern aligns well with our intuition about the retrieve and re-rank pipeline. The second observation has to do with the rate of increase that we discussed earlier. And as we said, there are bigger improvements at smaller depths. So what we did here is a curve fitting exercise. So we try to model and explain the form of the curve. And we did the following hypothesis. We say that the rate at which we discover relevant documents as a function of depth follows a power law distribution. And here we're using the Pareto distribution, and hence the name for this pattern. Just as a reminder, the power law distributions are usually used to model phenomena that there's uneven distribution. I mean, like wealth distribution or the frequency of certain words. In contrast to other distributions like normal, where there's a global average and then most of the values are around it. So by using this Pareto this Pareto distribution hypothesis, we try to fit the NDCG curves in. Here we just show 4 scenarios. The plots are the same as before. We have the ranking depth and DCG at 10. We have the BM25 baseline. The blue data points and the blue curve represents the actual measurements, the actual values. And the green curves and the green data points are the predicted values. So what you can see here is that we actually are getting a pretty good fit. Here we're using all 40 data points that we had available, but we can get a reasonably good fit even with a much smaller number of it if we carefully select the data points. The main reason behind this slide is that we find interesting the fact that the Pareto distribution can model that behavior, and we think that it warrants further investigation. The next observation has to do with the Oracle ranker. So here on the right, you can see a specific run on Wikipedia. The blue line at the top corresponds to the Oracle re-ranker, and as you can see, there is a gap between that and the rest of the re-rankers that we have selected. So one very straightforward conclusion is that there is still room for improvement for the existing set of re-rankers. The gap is big, but it's not that big in all cases, in all scenarios. But in all cases, this shows the room for improvement because the Oracle is the ideal re-ranker, as we said. And now we're going to try to see the re-ranker from a different perspective. So just to explain what I'm trying to do with it. So let's say that when we have a re-ranker, we provide as input, and especially cross-encoder models, we provide as input the query and the document. And for each document, we get back a score. So for example, here we have doc1, which gives scores S1, and so on. And then we're using these values in order to reorder the documents by putting first the most relevant one according to this re-ranking model. We also have the metric, which in this case, is NDCG at 10. And in this case, NDCG at 10 is calculated by taking into account just the first 10 documents. So we can view the re-ranker as a classifier and say that when the re-ranker assigns a score to a document, this is a positive prediction if the score is high enough to place it in the top 10 position, if we're talking about NDCG at 10, and negative otherwise. So from that perspective, we can have a confusion matrix and have defined false positives, false negatives, true positives, true negatives. And in this Pareto set of cases, we can say that the re-ranker acts as a classifier with some false negative rate, which means that there are actually relevant documents that get a low score. And that is also related to what we said earlier about the gap. There are relevant documents that the rankers cannot identify, but almost zero false positive rate, which means that there are no or very little, very small number of documents which are actually relevant but get a high score. Because otherwise we would see a performance degradation as we increase the depth. Now we'll move to the next pattern, which we call the unimodal pattern. It's the second most frequent. It accounts for 20.2% of the cases. Here we can see two phases. The first one is rapid increase, as in the case of Pareto, but then we reach a peak and then there's a decrease, usually at a slower rate. So by using the same analogy of the reranker as a classifier, here we observe a false positive rate. So the reranker starts to make some mistakes and actually assigns a higher score to irrelevant documents. So which starts to lead to performance degradation. And from a high-level perspective, it's like a struggle between two quantities. So the first quantity is about the good job that the ranker is doing. As we said, our modeling hypothesis was that the rate at which we discover relevant documents follows this Pareto law. So it decreases as we increase the depth. And that, combined with the true positive rate of the reranker, which is its ability to detect these relevant documents, gives quantity number one. The other quantity is about the relevant docs. So the probability of irrelevant documents increases as we increase the depth. And that, multiplied by the false positive rate, gives the second quantity. So it seems from a high level, from a high level perspective, that initially this quantity is much bigger. That's why we see the increase. Then these two effects are actually even. It's where we reach the peak. And then finally, the false positive rate starts to dominate, which explains this, this degradation in the score. The unimodal pattern is really interesting. It's very counterintuitive because, as we said, the most intuitive pattern is the previous one. We would expect, as we add more documents, to get better quality. And here we investigate some of the potential causes for this pattern. The first one is incomplete markup. And just to explain it a little bit, we know that certain datasets, like MS Marco and Beer, have very sparse relevance judgments. So usually for a query, we have a positive document and that's it. We don't have any other positive documents. We don't have information about negative documents, actually relevant queries. So it's likely, and it's something that we have also shown in a previous work, in a previous blog post that we did, that in a corpus, it's very likely that there are more than one, for example, positive documents. The reranker is able to identify those, promotes them to the top, but the evaluation is limited by these missing relevance judgments. In other words, we get an inferior score when we shouldn't. So even though this cause seems likely, there is a counter-argument. There are certain datasets like TRE-COVID where the labeling rate is quite high. It's over 90 or 95%. And we still get some unimodal patterns. So we think that this first cause can cause some fluctuations in the values, but it's not the main driver behind the unimodal pattern. Which brings us to the second point, and there are probably issues with the training of the rerankers, of the different rerankers. Again, from a high-level perspective, it seems that initially the reranker does a good job distinguishing between relevant and irrelevant docs. And then it starts to lose that ability as we increase the depth. So as we increase more and more documents and we feed them to the reranker starts to confuse it, starts to get confused. So another way to state this is that the relevant documents that appear in the deeper tail share some confounding characteristics with the actually relevant documents. And our explanation for that is that it has to do with the negative mining process of these models. As I said, here we consider cross-encoder models which take as their input both the query and the document and produce a score, as opposed to other models by encoders which queries and documents are processed independently and then are combined, and we get a score based on the representations. And a very typical negative mining process for the cross-encoder models is to do some shallow sampling, like get the top 10, 20 documents from a retrieval system, remove the positive ones, and keep the rest as the negatives. And as we move higher to the list, we get harder negatives, because these are documents that are semantically relevant, but they are not actually answering the query. One problem with this approach is that we conclude is that this does not present the reranker with sufficient diversity, both in terms of retrieval depth and the number of negatives. So in a sense, when the reranker sees just the top 10, 20, 50, and when at training time, and then we provide documents that are located, that are placed in the deeper tail, they behave like out-of-distribution data. And this is what likely confuses the reranker, and the scores that it produces are not reliable. And this is actually something that we've verified also with the training of our own elastic rerank model. And what we saw was that by expanding the retrieval depth and also increasing the number of negatives, we saw increased robustness and much better performance in our benchmarks. And now we'll move to the third pattern. It's called the bad fit pattern. It accounts for 7.1% of the cases. It's pretty straightforward. We have the BM25 baseline, and as we add more documents, we get worse performance. The likely cause is the reranker is out of domain for this particular data set that we experiment with, or it's a case where lexical search, in this case BM25, shines, like in cases of keyword searches. Here is an aggregate matrix with all the datasets and the different models. And here we have 3 more observations. First of all, you can see that there are certain rows where these non-optimal patterns are concentrated. First of all, it's Arguana, the first row, and to say 2020. There's an interesting connection between these two. They are both argument retrieval datasets. There's a paper from Thakur et al. In, I think, the last year's GAIR, which discusses neural retrieval models and their reduced effectiveness in Touché. And the fact there are some biases, for example, these neural models prefer shorter passages. We think that even though this paper is about neural retrieval and not retrieve and rerank, some of the conclusions apply to this case as well. But in general, it seems that these argument retrieval datasets are kind of special anyway. There's also 2 other datasets, Fever and SciFact. These are datasets that require background knowledge to support or refute a claim. So smaller models might be a disadvantage because they don't have that much world knowledge. And finally, there's another interesting case, Quora, which is a duplicate question task. So you provide a question as an input, and you expect to get duplicate questions in the response from the corpus. I mean, the 90% of the documents is less than 90 words, so the documents are quite short, and they have a very high Jaccard similarity. We observe a very high Jaccard similarity between the core within the query and the positive document. So the Jaccard similarity is the ratio of common terms to their union. So basically, that means that there's a lot of overlap in terms, which might explain a good score by BM25. Now we move on to interpretability. So what we do here, we're trying to explain these different patterns based on the score distribution. So what we do here is we get the scores, the documents at each depth. We separate them into positive and negative, relevant and irrelevant. And we aggregate the scores across all queries. And then we compute means and standard deviations. So the data points that you see here are the means, and the intervals correspond to plus and minus one standard deviation. Here we have this Pareto pattern, which is the one that we should have. It's the most intuitive one. What is interesting here is that there is a clear separation between the scores from positive documents and negative documents, which aligns well with what we see in the other plots, in the previous plots with the NDCG score. If we do the same for the unimodal pattern, which is another case here, we start to see an overlap between the positive and the negative scores. And this gets worse as we increase the ranking depth, which from that perspective explains why we see the performance degradation. And the last one is the bad fit pattern. And as you can see here, the scores for the positive documents are kind of all over the place, so which explains why we see this real bad behavior in certain cases. Now we'll talk a little bit about the efficiency versus effectiveness trade-off. So what you see here is this matrix where we have a selection of data sets and our ranking models. For this matrix, I have selected most of the cases that exhibit this Pareto pattern. We compute a quantity that is called gain at depth, which is simply the difference between the NDCG of after re-ranking at depth at a certain depth minus the NDCG score of the retrieval, in this case BM25. And as you can see, per dataset we have two columns. One is called max, which is the depth at which we achieve the maximum gain, and 90%, which is the depth at which we get 90% of the maximum gains. For example, for BG re-ranker v2 Gemma, we get a maximum gain at depth 300, but we get 90% of that gain at depth 150. Some observations. More effective models take advantage of larger depths, both max and 90%. So as we provide a larger pool of documents, they will do a better job identifying the positive ones, while the less effective models saturate faster. It's also interesting that if we look at the numbers, we can see that we can get 90% of the gains, which is the second column, by re-ranking 3 times less pairs, which is an interesting trade-off between efficiency and effectiveness. And also, if we look closely, we can see we can identify 2 groups of datasets based on the average score that they have for the 90% gain depth. So, as you can see here, the first four datasets, DPpedia, Hotpot QA, FICA, and Climate Fever, have an average score which is 100 or more. And the last 2, Fever and Try-COVID, have an average 90% depth of 51.7. And so, again, from a high-level perspective, that means that the re-ranking depth requirements for the second group are lower. And we think that this can be, it's not random, and it can be explained by the effectiveness of the first stage retriever. So what we have here are the NDCG 10 curves of the oracle. And we have, at the top, we have 2 representatives of the first group, and at the bottom we have the other 2 representatives of the second group. Just as a reminder, the NDCG score takes into account 2 dimensions. The first one is recall, because in order to have a non-zero NDCG score, you need to have some relevant documents in the top 10 positions, if we're talking about NDCG at 10. And the other one is ordering, because if you have two systems with the same number of documents in the top 10 positions, and system 2 has pushed most of them to the top, the second system will get, will attain a higher score. For the Oracle, the second aspect is not that important. It's a bit redundant because we know that the Oracle has access to relevance judgment, so it will do a perfect reordering. So in that sense, the NDCG score of the Oracle is a very good proxy for the recall of the retriever. So all that to state the kind of obvious fact that as the effectiveness of the retriever gets improved, the reranking depth requirements are lower, because at a smaller depth you will have any of the relevant documents anyway, so you don't need to re-rank more. It's kind of intuitive, but it's nice when theory and numbers agree. And now moving to this latency-aware analysis. So what we do here is to take into account the time it takes to do re-ranking. So what we do, first we start by measuring the time it takes to score 10 query document pairs, and we do that per re-ranker. And then we apply some sort of t-set sizing. So we defined as the small t-set size the time it takes for the most efficient model, here it's mini LM L2, L12, to get 90% of the maximal gain, what we discussed earlier. And we define the medium and the large t-set sizes relative to that. Medium is 3 times small and large is 6 times small. And all that leads to this plot where you see the blue vertical lines which represent the different t-set sizes. And we have the NDCG curves per ranker. One immediate observation is that the density of the data points is proportional to the efficiency of the model, because at the same unit of time, a more efficient model will re-rank more documents. It's something you can easily see for mini LM. And the second observation is that the winning model actually depends a lot on the latency requirements that we apply. So if we are very strict about latency and we follow this small t-set size, mini LM is actually quite a good choice, because this efficiency advantage allows it to climb to the first or the second position, but it's in general is quite good. On the contrary, a model like BG Reranker V2 GEMAC, which is a really strong model, is under that constraint, is at the last position, because it's really computationally heavy to run it compared to the other models, I mean. But as we become more flexible with latency, we see that it gets better and better. So overall, the thing is that in order to decide which one of them is the best model, you need to do some kind of plotting like this one, where in this case we're considering latency, and this will help to make a more informed decision. And now I'm going to conclude the presentation by discussing a little bit related work. So I'll start with a paper from the Neighbor Labs, where the focus of the paper was to compare cross-encoders with LLM re-rankers on top of Splade. Spoiler alert, cross-encoder seems to be quite competitive compared to LLMs, in this setting at least. So the authors consider 3 Splade retrievers, 2 cross-encoders, some LLMs, and 3 re-ranking depth values, 50, 100, and 200. What is relevant to our discussion here is that by looking at the numbers, you could identify some mostly Pareto patterns, especially for the out-of-domain distribution, because they're considering different, both in-domain and out-of-domain. The cross-encoders also have a smoothing effect, which I think is interesting, even though the retrievers can start can have a different starting point. Any differences are evened out after a certain ranking depth. And also that LLMs are effective at smaller depths, like if I recall correctly, it's 25 or 50, and then they exhibit this a Pareto-like pattern where there is saturation. Then there is a blog post from Vespa. The author here considers the focus of the paper was to assess the effectiveness of a log context called bear implementation. The author uses a retrieve and rank pipeline with BM25 as a retriever and log context called bear as the reranker, applied on the MLDR dataset. From our perspective, it's another instance of a Pareto pattern with signs of saturation at small depths, like 30 or I think it's 30 or 40. There's a paper from Meng et al. About ranked list truncation methods. So this kind of techniques are applied mostly for retrieval, and the goal here is to determine the optimal depth on a query basis. The authors here consider these techniques also for retrieval and reranking. And there is a setup which is called fixed K, where you decide the reranking depth beforehand for all queries. You can see the setup for the different retrievers and rerankers. From our perspective, when BM25 is used as a retriever, it leads to Pareto patterns, again, by looking at the numbers. And when Splate++ is used, we see more of a unimodal-like patterns picked at a small depth around 20. And finally, there is a paper from Databricks, which was published in parallel to our work. It's actually very close to what also has led to our investigation. I mean, what the authors are doing is to challenge the assumption of increasing gains with depth. So the observed rerankers at the extreme, even by considering the top 5,000, if I recall correctly, documents. They're using a set of retrievers and rerankers, 8 datasets, some academic, some enterprise ones. As you can see from the title of the document, it's Drowning in Documents. They focus a lot on the unimodal cases. From our perspective, especially for the academic datasets, there are also, again, by looking at the numbers, you can see that for the enterprise ones, we have a combination of Pareto and unimodal. It's quite interesting. I mean, we have very similar conclusions, very similar findings. We have very similar conclusions also about the causes, the underlying causes of unimodality. Yeah. That's it. Thank you.
Question already?
Very beautiful presentation. I love it. You covered everything in depth. I'm blown away. Beautiful presentation.
Thank you.
I first observed this pattern, I think, over a year ago with a customer. So I'm at OpenSearch, and you may have heard of us. The customer was complaining, I can't get better results by doing re-ranking. So, well, how many are you re-ranking instead of 1,000? Why are you re-ranking 1,000? Because 100 gave bad results, so I cranked it up. I said, well, what is your first round retrieval? I said, oh, we had a very fancy first round retrieval thing, but we threw it away and we put in plain KNN search. So, well, there's your first error. You probably want to be doing hybrid search. Secondly, you probably want to be using your old retrieval system. And I saw this pattern at other customers too. And I think I posted a blog post last year entitled "Garbage In, Ranked Garbage Out," which is exactly the phenomenon you're talking about. And so, how are we going to get this message out? People seem to think, oh, you just crank the power up, and AI will solve the problem.
Yeah, that's a good point. I mean, what this investigation shows is that if you're lucky enough and you just plug certain components in a pipeline, 70% of the cases you'll be okay. I mean, you will get, even though it might not be optimal, because after a certain point, you might get saturation, and even increasing the depth, you won't get the degradation, but you're not getting any benefit as well. So, but that happens in 70% of the cases. For the rest, 30%. I would say that this highlights the need for custom evals. I mean, it shows how important it is to have to think about the retriever and how compatible is the reranker with the retriever, how efficient is it, how effective is the retriever. Yeah, I don't think there's an easy way to know beforehand what is the right combination of tools. Having something, having some custom evals, I don't know, even through LLM as judge, I don't know, this is a viable option if human annotators, it's not very feasible to have human annotators. But yeah, in short, you need some kind of evaluation.
Well, yeah, I guess the big issue here is that those of us who have lots of gray hair and know the traditional techniques say, oh, the traditional techniques are pretty good. They're not perfect. But then we have people come in and say, oh, throw them out. You can start from scratch and do much better, which is not true.
Yeah, I agree with that. Yeah.
So how are we going to educate the search community about this kind of thing? It seems like the data scientists all want to use very simplistic approaches.
That's a good question. Yeah. I'm not sure about the answer right now. Yeah, you need to think about it.
Anyway, your paper is a great foundation stone for that discussion.
Yeah. Thanks for that. Yeah.
So you highlighted two possible reasons for the unimodal distribution, and I think one of the reasons was missing labeled data, and the other one was maybe shortcomings in re-ranker training.
Exactly.
And you said it's probably the second. Did you do any manual kind of verification or evaluation of the sampled results that you came to that conclusion? Or
actually, for both of them. For the first one, as I mentioned, there's a paper from Thakur et al. Let me go back a little bit. It's this one, where the authors, apart from explaining the behavior into SE, they also have added some relevance judgments into this data set. So, just to explore a little bit, I took the extra relevance judgments and applied them into the cases where I see unimodal patterns, and this was not the solution. So I kept seeing the unimodal patterns, which naturally leads to something more systematic. For the second point, it's something that we actually integrated into the training of our own elastic re-rank model. I mean, this research was done in parallel, and when we saw, initially we thought that there was something wrong with the code. When we verified that it was not the case, and we did some further research, and we arrived into those conclusions. We applied those learnings into the training, and we saw increased robustness and improved performance. So this is this is why we think the second cause is the more likely.
Maybe a second question then. So your elastic re-rankers seem to be pretty good or even superior to the others in your graph. Can I just use that now, or is that something I can just grab and use in my applications? Or
it's available in the stack, yeah. But this is just I'm not promoting elastic rank here. It's just this particular run. But yeah, it's quite robust, yeah. But it is available in the stack, in the elastic stack.
Any other question? Looks like not. So let's thank our speaker again for a nice presentation. Thank you.
Thank you.